Welcome back, everyone, today. So today it's our pleasure to have one more machine learning seminar directly from the Newton Institute. And today we'll have Arturo Castellanos who will be talking about kernel trace distance, quantum statistical metric between measures through RKHS density operators. Thank you, Arturo.
So thank you for the invitation to this One World ML seminar, and also for the Newton Institute to host me for this month. So I'm going to present you work about kernel trace distance. It's a joint work with Anna Korba and from NSA and Pavlo Mozarski, Isham Janati, my supervisor at Telecom. So I'm a third-year PhD student, and I'm looking for opportunities to continue in academic research after the end of the year. So this is briefly the outline of this talk. So I'm going to first give some motivation to introduce our new distance. Then I will show how to compute it in practice. I also show some theoretical results on the convergence rate and the robustness. And finally, I will show some experiments. So there's two motivations. So the first one is about IPM. So our setting is we want to look at distance between probability distribution. So if you have mu and nu, two probability distribution over some space, but let's say it's RD, but it could be over space. And so an integral probability semi-metric is defined this way. So you're gonna take the expectation of some function f when applied to variable drawn from mu, and you're gonna look at the difference when instead you apply f to some variable coming from mu, and then you're gonna take the supremum of this difference over all possible set of function f. So if you choose a different set of function f, you will give you a different well-known distance. So if you pick a set of function of bounding function in some nice Hilbert space, which are some nice property called reproducing kernel Hilbert space, then you recover the maximum mean discrepancy. If you take functions which are one Lipschitz with respect to some cost distance C, you recover the one Wasserstein distance. And if you take function bounded in values between -1 and 1, you recover the total variation distance. So then one can ask, so of course, as your space F is bigger and bigger and more rich, then you have a stronger discrimination power. So if it's rich enough, actually you can have a proper metric. So if distance of mu and nu is equal to 0, it means that nu equals mu. But also if the space is bigger, then the computational complexity is harder, and also the statistical convergence rate may be slower. So for instance, for the maximum mean discrepancy, you get a relatively fast convergence of between the empirical distribution mu with n samples drawn from mu and the population version mu. But for the Wasserstein distance, you will have curse of dimensionality, so you are something 1 over n to the power 1 over d. So for big dimension, it's not going to be great. So one question is, can you have a space of function which is bigger than MMD? And when does it start to have curse of dimensionality or not? And another motivation is with respect to MMD. So basically what kernel methods do is you use a feature map 5 that sends each of your points in RD to a vector of features in some Hilbert space H. And then you can compute what is called the kernel inner product, K between x and y, which is just the inner product of phi of x and phi of y in the RKHS H. And in general, you have a direct formula for k of x and y, so you don't need to compute phi of x and y. And what the MMD does is use actually a representation of your distribution mu called kernel mean embedding. So it's just the average according to mu of the phi of x. And then you took to get the squared MMD, you took the squared Hilbert norm between the mean embedding of mu minus the mean embedding of mu. So if you develop this product, you can see these two first terms are kind of like what physicists would call energies. The internal energy of mu with the inner product with itself, and same for mu. And then you retrieve some term, and if mu is close to mu, then you can imagine that it will cancel the two first terms. And it's easy to compute this inner product. It's just the double integral or double sum with the k of x mu. So, but one strange point is that mu and mu may not have the same order or the same norm. So you're comparing two embeddings which don't have the same norm, and that we will see has some impact later. So what I want to consider instead is different embedding. I will call it RKHS density operator, which is again the integral over mu, but of phi of x tensor phi of x instead of just phi of x. So instead of the mean, you can see it as a covariance. So in this talk, we will also assume all the phi of x have norm equals to 1, just like in quantum information theory. So this is true for many kernels, like the Gaussian kernel, the Laplacian kernel, the inverse multi-quadri kernel. So this operator is positive semi-definite. And as you see, if you take the feature map, which is a tensor of phi, then it's also some kind of kernel mean embedding, but with a different associated kernel. It's with k square, because if you take the inner product of tensor product, you get the product of the inner product. And so this was this point of view was initiated by the work of Bach in 2022, where he applied the quantum Kullback-Leibel divergence on this operator. So the idea is not to see it as a mean embedding, but now that you have positive semi-definite operator, covariance operator, then we can use all kinds of distances and metrics, which you apply to matrices and operator usually, which you wouldn't do on a vector representation. So the one we want to consider is the P-shuttle norm. So the P-shuttle norm is just, you can see it if you do the singular decomposition of your operator T, it's just the P norm of the singular values of T. And it has a nice property that there's a dual formulation. So if you take the conjugate Q of P, you can rewrite the norm as a supremum of the inner product of T with some mu, such that U is also an operator in the same space, and the Q norm of U is 1 or smaller than U. And so here the inner product is the one that works on matrices and operators, so it's a trace of U adjoints times C. So then you have classical properties like if P is smaller than Q, then you have the P norm is bigger than the Q norm, and you have also all those kind of inequalities that we will use later. So the new distance we want to introduce is what we call the kernel trace distance, and it's just the one-shuttle norm of the difference of the RKHS density operator, sigma mu minus sigma nu. And here we can see it's normalized with our hypothesis of phi of x with norm 1. We get that the shuttle norm of the RKHS density operator is always equals to 1. And if the embedding is injective, so if the kernel is rich enough, this is a metric. And by the duality, we can also prove that it's an IPM. So it just, if you remind the duality of the Châtel norm, you apply it with some mu to sigma mu minus sigma nu. So you can split by linearity of the inner product. And then you can also have linearity of the integral and the trace. So then you recover that it's an IPM with respect to the this space of function F1, which is phi of x star u phi of x, with a u that has operator norm equals to 1 of it. So these functions are bounded by 1, and there are also two Lipschitz with respect to this kind of kernel distance, Hilbert norm between phi of x and phi of y. Okay, so why did we want to study this distance? Because there's a lot of relations with other distances. So actually, as I said, it's some kind also of mean embedding, not just a covariance embedding. So you can say the two-Châtel norm is actually MMD with chi squared. So then we directly get that MMD is smaller than the kernel trace when you use it with kernel k squared. And most importantly, why we wanted to study it is there is a famous quantum inequality called Funks van de Graaff inequalities, which basically say that you can relate this distance to the kernel Burr-Wasserstein distance. So what is the Burr-Wasserstein distance? It's a special case of two Wasserstein distance with two norm between two center Gaussian. So if you have two center Gaussian, the only information about the Gaussian that matters is the covariance. So then the Wasserstein distance become a distance between covariance matrices. And if you plug the RKHS density operator, then you get the kernel Burr-Wasserstein distance. As we said, the spatial function is included in the spatial function of the total variation distance. You also have the quantum pin-square inequality when you apply the quantum relative entropy to sigma mu and sigma nu. And finally, so if you use a Gaussian kernel, for instance, you can relate it to the Wasserstein distance with Euclidean cost using a factor 2 over sigma, where sigma is the bandwidth of the kernel. So in a way, we have something in between MMD, some kind of MMD, and some kind of Wasserstein distance. So now how to compute this thing in practice. So because RKHS density operators are often infinite dimension space, because the interesting kernels are the one with infinite dimension. And for the two-Châtel norm, you can just develop the inner, it expresses the inner product. So there's a nice trick to compute it, but here we have the trace of an absolute value of difference of infinite operators, so it looks complicated. But actually, when we think again about this, if you use empirical distribution, then the empirical density operator are finite sum that only live in a finite dimension subspace. And so we developed a new kernel trick to be able to compute it. So there's a classical trick that if you have your points and you stack them in a matrix Z, then if you want to compute the kernel gram matrix of all the inner products, you just take Z star Z or Z transpose Z. And on the other end, the covariance will be Z times Z star. And if you have an eigenvalue and vector of the covariance, when you apply Z star on the equation, you can see that you also have that Z star V with lambda is the eigenvalue and vectors of K. And if you can do it the other way around, and if Z star has the correct rank R, then you don't lose any eigenvector, so they have the same spectrum with also the same multiplicity of the eigenvalue. But in our case, we have a difference of covariance instead of one covariance. So can we do the same? The answer is yes, and we got inspiration with quantum mechanics that have some quantum states have some amplitude and sometimes use imaginary numbers. So what we do is we rescale the feature with 1 square root of their weight. And for the other distribution, for the y points, we had the I imaginary number. And so when you actually tensor the whole thing, then you will get that I over square root of m phi yj tensor itself. You just multiply the constant, so you recover minus 1 over m times the term that you find in the covariance. So then you can express sigma mu minus sigma nu as a ZZ star. So we say we wanted to have distinct points. So if you have just 2 points, you just use square root of 2n. You need to check your weights, but basically what you get is a difference kernel matrix that looks like this. On the diagonal, you have the usual kernel matrix of k of x, and then another block with minus k of y. And on the other blocks, you have the cross kernel matrix with some imaginary part. So it's a strange matrix which is symmetric, but not Hermitian, but still complex. But we know that there's the same spectrum as C, and C is nice. It has real eigenvalues. So there's no strange thing happening with this complex matrix. And if you do the singular value decomposition in cubic times, you can just get the values and compute the distance by taking the p-norm. So now I want to talk about some theory. So what is the convergence rate of this kernel trace distance? So we have, again, a problem because we have infinite dimension. So we have infinite number of eigenvalues. We cannot, like the operator norm, just focus on the biggest one and do concentration inequalities. We cannot do the inner product trick like MMD. But what we can do is, well, first, if you think about it, that the trace is equal to 1, as we say, and the eigenvalue are positive, so the smallest eigenvalue should converge to 0. So the idea is just to use some PCA projection to reduce to finite dimension and drop the smallest eigenvalue. So if you use the projector pair sigma that project on the top L eigenvalues on sigma, then you have a covariance operator in a finite dimension, and then you can use order inequality and relate to the Schatten norm, which has convergence rate exactly like MMD. And also we assume a nice decay of the eigenvalues that will give faster rates. So there's two kinds of hypotheses. So either the eigenvalues decay as a polynomial, so the lambda I are of order I minus some alpha. So this work by Starger and Crawford on kernel PCA that says if you use the projected covariance instead of the true covariance, first in Schatten norm 1, it's equal to the sum of the lambda I after the index L. And actually, this sum you can relate it to the integral of the polynomial decay function. So it's easy to bound. And if you take the Schatten 2 norm, then if you think about it, the lambda I square, they have decay of 2 alpha instead of alpha. So you replace alpha by 2 alpha, theta by 2 theta, and the square roots erase some 2. And this is the new result we get, is what happened when you mix, you use PL sigma on mu n on the populational sigma mu when you mix the two. And we got similar kind of rate. So the other hypothesis possible is also faster rate of exponential decay, and then it's really much faster. And so, thanks to this result, we managed to prove this theorem. So basically, the kernel trace distance for polynomial decay will have n to the power minus 1/2 rate like MMD plus some 1/2 alpha. So for big alpha, it's close to MMD, but for small alpha, it's slower. And if you have exponential decay, then if you don't care about log term, it's just like MMD. And this gets bound by inequality on the kernel Wasserstein distance as well. So the quick sketch of proof of the quick idea of the sketch of proof is, okay, so I use sigma and sigma n to have a lighter notation. So the first we decompose using the projecting matrix of sigma n of sigma n, and then you have the term in between when you use the triangle inequality, where you have hybrid, you mix sigma projection on sigma n with sigma, or vice versa. So the first term we already saw the rate. The second, the last term, it's the same, it's just the empirical version. You can relate it by a result by Blanchard and others. And then there's the two of us term. For the two of us term, since you projected them on a subspace of dimension L, you can just order as inequality. And then, so you're gonna have the MMD rate with the Chaton 2 norm, plus you pay the cost of square root L because of the inequality. So you pay this extra cost. So then you have the second term is, the other term is also the same trick. And when you have everything, you have to pick L. So that's, so for the first and last term, it's good to have L as big as possible, to be as close as the true sigma. But for the other term, you want L small because you project on this subspace. And if you, so okay, if you pick the right L, you get the theorem we showed before. And so now I want to show some robustness property. So first, again, compared to Wasserstein, so in this setting, we have a distribution P, but actually we replace epsilon proportion by another distribution C that contaminates it. So what happens if you replace P by P epsilon? We can show by the triangle inequality easily that it's going to be smaller than 2 epsilon. So it's relatively robust. If epsilon is small, it's not going to change much your results. But if you use the Wasserstein distance, if epsilon is very, very small, but see it at some point very far away from your distribution, then the distance will explode. And now the robustness compared to MMD. As you have seen before, so the MMD, the 2 Chaton norm, is going to be smaller than the 2 energy, the square root of the 2 energy of your distribution. So to remember, the energy is the integral of the k of x and y when x and y comes from mu. So if mu is a Dirac, then it's just 1 point during the inner product with itself. So it's going to be a high similarity, so it's going to be a high energy. But if your distribution is uniformly flatly spread over some support and has high variance, then if you take, for instance, the Gaussian kernel, when 2 points are far away, they have an inner product of 0 almost. So the energy is going to be very slow. very low. So that means your MMD is actually just low because your distribution are very flat. It doesn't mean that they are far away. It just means it's just the fact that they are flat makes the distance lower. And this may be a trouble because you want to tune the bandwidth sigma with respect to the variance of your distribution, but also to the gap between the two distributions. So when you vary sigma from, for instance, at infinity, then everyone is similar to each other. Every point is similar to each other. When sigma goes to 0, then almost all the points are orthogonal to each other. So you would expect, when you change sigma, you would expect something like the kernel trace distance, that you have the highest value, and then it goes to 0. But with the MMD, you have two regimes, because at the same time, it decreases like the kernel trace distance. But at the same time, if you have really low sigma, then you have also low energy. So in practice, you need to pick the right spot, and maybe you don't know in advance the right spot. So another example, so if you admit some kind of density, which look like one mode of truncated Gaussian, you can use Gaussian kernel and compute the two distances. So if you have a pin Q that has a mixture of two modes, which is exactly the same as before, but they are put at different locations, then for the total variation distance, you will have 1/2 of your previous distance and 1/2 again. So you will recover the distance with one mode. And the same happens with the kernel trace distance. But with the MMD, you see that the MMD square is divided by 1/2. And this is because when you have several modes, you lowered your energy, you have a bigger variance. So now I go to application. So here we do some gradient flow where you want the red cloud to move the bluish target. So you can see, so we use the Laplacian kernel because it's better than the Gaussian kernel for this. And you can see that both matches the target, but when you use the MMD flow, somehow the cloud spread, and there are some points that are going outside the image, but do not converge yet. And this is because of the internal energy that tends to repulse the cloud of points. Let's say if you are really spread out, you will diminish MMD anyways, even if you don't match the target. So this is one example of the previous point. And finally, I want to show some experiment on approximate Bayesian computation. So it's just like a normal Bayesian computation. You have, as usual, some model parameterized by theta and with some prior distribution pi on your theta. And but maybe, and you want to compute the posterior, but maybe the posterior is hard to compute. So what you do instead, you're gonna draw some theta I from your prior. Then you're gonna draw some y's from this p theta I. And then you look, does the y match the x? Does it look like the real data? So you take the distance between the two, and it should be between some threshold epsilon. So that's we done, and so we use n original points, and the same for the generated points. And we did the 10 iteration of theta i's. And we did it in a robust setting. Where, so we had the Gaussian center at 1 with variance 1, and we replaced 10% with a Gaussian center at 20. And we also have a model of Gaussian, so parameterized by the mean. So you want to recover the mean equals to 1. And the usual Bayes rule will give you some posterior that looks like a Gaussian of almost the empirical mean. But the empirical mean is close to 3 because of the contamination. So you will not recover 1. And similarly, if you do the Wasserstein distance, it will always be very high. So if you have a small threshold, it will reject all samples and will not give you any posterior. So instead, we try to use the MMD and kernel trace distance with Gaussian kernel, and also with the energy kernel, which is unbounded and does not fit our assumption at the beginning, but we try also with this one. And we see with different thresholds that MMD accepts a lot of points because of what we say, because of the variance. It accepts even if the two distributions are not the same, are not close. And also, so if you take epsilon lower than 10%, the kernel trace distance rejects all samples. But if you take it higher with some taking into account some statistical error, then you get good result with the kernel trace distance. So it feels like it detects the amount of contamination in your data. Okay, so to conclude, I will introduce a new IPM distance that avoids some MMD drawbacks at the price of higher computation, has many relation with other distances. We also use a new kernel trick that may be of independent interest. So we had some bounds on the convergence rate, but we don't know if we can improve the proof and get better rates and also lower bound. And yeah, we show some robustness property as confirmed by the experiment. So I thank you for your attention.
Thank you very much. Thank you. Any questions from the online or in-person people?
Yeah, let me go first, otherwise that looks stupid.
Yes, please.
So on slide 16, I'm not sure I understood this. So you were talking about formulating a hypothesis with the eigenvalue decay, but from what I remember, so these are eigenvalues of a kernel. So I mean, the sigma is basically an integral over a kernel that's convolved with itself, right?
Yeah, so it's the eigenvalue of sigma mu. So it depends on which kernel you pick, and also which distribution.
Yes, and I think there are actually results like this. We wrote a paper on this recently. We used these results. I can point you to some of them where actually you do get polynomial decay for Matern kernels. And I forget what the condition is on the measure, but you do normally get them for specific cases, and you definitely get it for the Gaussian kernel as well. I forget again what you need on the measure, but there are conditions, like there are fairly well studied settings where you definitely have these hypotheses satisfied.
Yeah, interesting to know. I know it's for a unit cube with Gaussian kernels. It looks like you have a nice decay, but I didn't know about Matern and our distribution.
The other parallel, so we use this in a completely different setting. I don't know if this is useful at all, but the way you constructed these sigmas, you can think of what you have done as computing the difference between covariance operators of Gaussian random elements on RKHS. So you've implicitly constructed a distance that way. I don't know if that gives you any further insight into the analysis. I can show it to you. It probably makes more sense to do that one-to-one. But what you're doing implicitly could be recast in this way.
Yes, actually, when you do the Wasserstein on the RKHS, it's the kernel Wasserstein. So as I say, this distance relates to it. And
oh, I guess I'm saying you're defining you're implicitly defining random variables on an RKHS and then looking at their distance. That's one way of interpreting what you've done as well, which is quite interesting, or which might be interesting anyways. Maybe not.
Yeah, sure. Thank you.
Well, actually, my questions are much more naive than that. So, what I didn't, so you were sort of bounding from below and above your distance DKT between Wasserstein on the right-hand side,
yes.
if I understand correctly, and the MMD on the left-hand side. It's actually the idea.
Yes.
One question I have is there like is there some result in terms of like invariance per transformation of your data of X associated to your distance? Like for instance, the Wasserstein, it might be a drawback or it might be on the contrary what you look for, but they are not invariant per transformation for the on X and Y, whatever that is. And your distance, do you have invariant? Because the total variation distance is invariant. And are there some results? Are there something like super well known and things like that? Or?
So if you use the translation invariant kernel, you use just the distances between the points, so you're gonna have just isometric invariance. So probably with the Wasserstein, you also have isometric invariance. So it really depends on the distance in your kernel, but then I don't think you can get more than this.
Okay. And then when you were talking about the convergence of your results, like the sigma, so it was if you that I was a bit lost. So you what did you do? You were replacing your sigma n. What was sigma n? I don't know whether you defined it or not. So.
Okay, so I just used, because it was a heavy notation, I just replaced sigma mu n by sigma n, sigma mu by sigma, just population and empirical. And yeah, so basically, the good point of using this distance rather than for instance, divergence, is that we have the triangle inequality by using the norm. And so we have, it's easier to prove the convergence rate. You can just use triangle inequality. We also use it for the robustness. That's why we also try to do this distance. I hope it answers your question.
I'm not sure, but I guess because probably my question is really like nonsensical. But so what does it represent? This sigma minus sigma n? Is it the distance between mu and mu n in terms of your? Is it the same as dkt of mu and mu n? So this is dkt of mu and mu n. You're saying?
Exactly. There's the same dkt of mu and mu n, and the Chaton norm of sigma mu and sigma mu.
Because, so for instance, so just to go back to the statistical results I know, so you get n to, for instance, in Wasserstein, you get n to the power minus 1 over d, without any assumptions on smoothness of mu, for instance. But then if mu is smooth, then you're not going to approximate mu by the empirical measure, you're going to approximate mu by something else, and then you get a better rate of convergence in Wasserstein. So the curves of dimensionality can be sort of weakened by the fact that you have smoothness on your distribution. And this is something that's hidden in your results. So sort of essentially it's hidden in your theta or alpha term, or is it something that's can you do the same, or does it make sense? Or
I know one example of the unit cube where you have a good decay. And for the Wasserstein, you don't have good decay if you use the empirical measure, as you say. But I don't know if we can say how smooth it's gonna be on the unit cube. But we didn't consider the smoothing the density, but that could be interesting.
All right, other questions or comments?
Well, just a comment. So, I mean, there are plenty of things to do now. I mean, you can apply this on different domain, like use it as a loss function, for instance. Have you planned something like that?
I was thinking of extending the kernel trick, and yeah, when we thought of experiment, we could think about using calibration or other things, but in the end, we focus on ABC. So yeah, there should be many.
You could use this now as a loss function in problems where you want to estimate the distribution.
Yes, we saw it's in GAN. They use MMD GAN, things like this. Yeah, I would be happy if someone wants to use this system.
All right. So any questions or comments?
Yeah.
Yes, Paul. Yeah.
In one of your experiments, you show some interpolations between two ontological distributions. You show that the interpolation is nicer that with MMD. Right. You have a figure with interpolation.
You mean when you change the bandwidth?
No. I mean when you transport from distribution to
the particle flow?
Yeah, the particle flow one, exactly. I just wanted to know how easy it is to compute. Like, is it like the interpolation between the...
So here it's n cube instead of n square. So
instead of n square.
MMD is n square.
MMD is n square
because we have a bigger space on function, it's harder, and we have n cube complexity. So depending on the size of n, the setting, it's maybe better to choose one or the other.
Okay. So n cube is for you, and okay.
And Wasserstein is also n cube.
N cube as well. Yeah. That's correct. N cube, it's not that big. Okay.
All right. Since there are no further questions, then either online or in person, right?
Yes. Oh.
Okay, let's thank the speaker. Thank you very much to everyone, and see you soon. Yeah, thank you.
Thank you.